Alrighty. Now we are on lesson 6. We're really getting into our unit now. So we talked about, okay, what does it mean to create equations, how to represent equations. We talked about how to graph equations. And so now we're really pushing the envelope a little bit further. So today we're going to be talking about what it means for two equations to be equivalent. Think about where equivalent comes from. Think about the word equal, right? These things are words that we can use both in math and outside of math. So start to build those connections, right? And identify how we can transform one equation to another so that we're still have this balance that I was talking about before, right? When we're creating our equations, we always must remain in balance. And so we'll talk about that a little bit further as we get into the video. So our vocabulary word today is equivalent equations, and I'll talk about that in a little bit. And so for your first activity, you are taking a look at two expressions that I gave you, and you're going to evaluate the expression when n equals 5 and then when n equals 7. We'll go through when n equals 5, just so a little bit of a math review and practicing our order of operations. And then you're going to take a look at what is happening at the results, right? So for the first one, we want to evaluate the expression when n is 5. So when I see that, okay, I know that I need to substitute in 5 into wherever I see n. So I know that I have 5 squared minus 9 all divided by 2 times 4 minus 3. Okay, so now I want to simplify my expression. Okay, so going through each part together, right, we have 25 minus 9 all over 2 times 4 minus 3. Right? 5 squared is the same thing as 5 times 5. And 25 minus 9, right, gives me my top value, which is 16. 16. I can also simplify the bottom. 4 minus 3 gives me 1. 2 times 1, right? So I have 16 over 2, which gives me 8. Okay, that is for my first equation. And let's take a look at our second equation. So I have, wherever I see an n, I'm going to replace it with a 5. So I have 5 plus 3 times 5 minus 3 all over 8 minus 3 times 2. 5 plus 3 is 8. This is multiplied by 5 minus 3. 5 minus 3 is 2. Remember, when it comes to order of operations, multiplication first, right? We have our, think back to elementary school, PEMDAS, right? Parentheses, exponent, multiplication and division, addition and subtraction. So we have multiplication first. We have 8 minus 3 times 2 is 6. This gives 8 times 2, and then 8 minus 6 gives me 2. 2 divided by 2 gives me 1. 8 times 1 also gives me just 8, right? Practicing our elementary operations. And think back to what you did in elementary school and middle school. Wait, where does that come from? And so, okay, so this gives me 8. The second one gives me 8. What do you see now? What's going on here? So why don't you see what happens when you evaluate the expression when n is 7? And what do you notice? Right? What do you notice about those results? And if you tried a third value for n, like 0, like 5, sorry, we did 5, like 10, like 15, what do you think is going to happen? And so that's what we're really exploring today, what it means to have equivalent expressions. And so for the second activity, you're taking a look at, all right, what equations could represent the relationship between the ages of two children in the family described? And remember, when you're creating equations, you want to use the math type button here. And you can use the keyboard if necessary. A family, for family A, we have the youngest child is 7 years younger than the oldest, who is 18. Okay, so I want to create an equation that represents a relationship with the ages of the two children in each family described. Okay, so the youngest child is 7 years younger than the oldest, who is 18. Okay, so if the oldest is 18, I know that the youngest has to be 7 years younger. So I know that 18 minus 7, oops, I don't know where my mouse went. 18 minus 7 should give me the age of the youngest child. And so I can either do that math or I can represent it as a variable. I'm going to do the math. So 18 minus 7 gives me 11. And so that means the youngest child is 11 years old because they are, because they are 7 years younger than the oldest, which means you did 18 minus 7, right? In your description, you want to describe what did you do. And remember, an equation doesn't necessarily have to have a variable, right? Here's an equation where there isn't a variable. You can create an equation where you have a variable, and that's completely fine too, right? Family B, the middle child is 5 years older than the youngest child. Okay, so if I set, let's define our variables. If I set M to be the age of the middle child, and I set Y to be the age of the youngest child. And all right, let me create my equation. So the middle child is 5 years older than the youngest child. So the youngest child, so all right, the middle child is 5 years older, sorry. So that means Y plus 5, right? The age of, the age of the middle child is the youngest child plus 5. Right, so we can think of it like that. And so you create the second equation and describe what's actually happening. And think about your equations themselves. Should they be similar to each other? Should they be different than each other? What facts are you working with? And so that's what you want to do as you're moving forward. And so then, right, and so then Tyler thinks the relationship between the ages, the children, and family B, right, that I was talking about here, is described as 2m minus 2y is equal to 10, right? I took the variables from the previous one. And so, right, you want to explain why this is true. And so think about the structure of the equation that I had on the previous slide and the structure of the other equation that you're going to create for yourself. So what do you see is similar here? Right, we have 2m minus 2y equals 10, and I have m equals y plus 5. And so think about some of the operations we were doing, right? We always want to keep things in balance. And so equivalent equations have exactly the same solutions or exactly the same values that make the equation true, but they may look different, right? So they look exactly the same, but they may look different. And so when you see something like this, right, are all these equations equivalent to each other? And so you want to describe which ones are and making sure you explain why, right? So we have our, I lost my pencil thing again. So if I have my equations listed here, how are these equivalent to each other, right? If we start with a equation at the top here, right? If we decide this is my equation that I'm starting off with, let's see if they're equal to each other. And so, all right, so I know that 3a plus 6 equals 15. And remember, we always want to keep our balance. Our balance here is that we have 3a plus 6 equals 15. We have to keep a balance. And so whatever I do to one side of my equation, I have to do to the other side of my equation. And so what I can do here is I can subtract 6 from both sides, right? Whatever I do to one side of the equation, I have to do to the other. And this gives me 3a equals 9. Oh, that looks familiar, right? I know that these two equations are equivalent. And so then we can start looking forward, right? Then what about a plus 2 equals 5? Is that something that is equivalent, right? Can I adjust this in any way? I know that 3a, also know that 3a plus 6 equals 15. And I'm looking at this one. And so I have a 3 next to the a here, but I have no 3 here. And so whatever I do to one side, I have to do to the other. So let me try multiplying by 3. 3 times a plus 2 is equal to 3 times 5. Right, whatever I do to one side, I must always do to the other side. Remember your distributive property here. 3 times a is 3a. 3 times 2 is 6. 3 times 5 is 15. This looks exactly to what we were talking about before. And so equivalent equations are just equations that have some sort of manipulation done to it, some sort of operation, right? We see subtraction here, and then we see multiplication here, or you could even say this is division, right? I could divide each term by 3 here, and that will give me equivalent equations. This is multiplication, and see what is happening here. Is the last one also equivalent? Right, see how they are related to each other. And then when you go to the next slide, right, where you're going to continue to practice what it means to have equivalent equations. And 6.3a puts it all together with everything we've been talking about before, right? Noah's buying a pair of jeans using a coupon for 10% off. I mean, we all like to do that when we are going shopping, especially for jeans, super expensive normally. Right, the total price is $56.70, which includes a $2.70 in sale tax, and Noah's price can be modeled by this equation. Think back to our previous lessons. What does the solution to the equation mean in this situation? Is 70 a solution to the equation? Is 60 a solution to the equation? How do you find that? Those are from our previous lessons in lessons 4 and 5, 3, 4, and 5. And so now we're taking a look at creating equivalent equations, right? And you have 3 questions to answer at each point. For question A, right, we are, for each equation, you're answering 3 questions. I'm sorry. And so when you have your equation A, right, what is done? Here's our original equation. And so what has been done, right, what operation has been done so that it looks like this? Right? Did I multiply? Did I divide? Did I subtract? Did I add something? Right? See what's happening at each point. And then look at equation B, right? What is happening here? And so I filled in some parts for you, so just to get you comfortable with what's going on, right? You want to know, okay, what has been done to this equation? Did I multiply? Did I divide? What does this actually mean in the context? I know that if this is the price represented in dollars, if I multiply by, I did tell you, so what should I multiply by? If I multiplied by something, the price expressed in, this represents the price, it represents the price expressed in cents instead of dollars. And does this have the same solution? And so this is your key point, right? If it has the same solution, then you know that it is an equation. Handwriting just died over there. That's an equivalent equation. And so if it has the same solution, then you know that it must there we go. It must represent the same equation, just written in a different way. And so with equation B, you also want to see that, right? You can see what has been done. I've subtracted $2.70 from both sides. And so what does that actually mean in context of this equation? And what is the solution? And therefore, is it an equivalent equation? So you want to do that for the next 2 slides. And last but not least, the lesson summary, which summarizes everything that I was going over and adding some more key points. So I will see you in lesson 7.